All right, hi everybody, welcome back. In this video, we are going to start Unit 5 of AP Calculus. Unit 5, Analytical Applications of Differentiation, and we're going to start with our lesson on using the mean value theorem. So we'll start by introducing the mean value theorem for derivatives, which you see written right here in your notes sheet. All right, the mean value theorem for derivatives says if y equals f of x is continuous at every point of the closed interval from a to b and differentiable at every point of its interior, the open interval a to b, then there is at least one point c in the interval from a to b at which f prime of c is equal to f of b minus f of a all over b minus a. So let's break this down and make sure we understand exactly what it's saying here. In looking at this, consider what it says. It says, if we have a function that's continuous and differentiable, okay, on an interval, and that's where we get right here. If we have a function, it's continuous at every point on an interval and differentiable everywhere in that interval. Then, the slope of a tangent line at some point c, that's this right here, f prime of c, there's at least one point c in the interval. At least, notice there can be more than one, just so you know that is definitely a possibility, must equal the slope of the secant line through the endpoints of the interval, which is what we see here, our good old slope formula, our average rate of change. And so the mean value theorem, if you think about this from a lot of different perspectives, it says that there's at least one place in an interval when that interval is continuous and differentiable, where the instantaneous rate of change at that point is the same as the average rate of change over the interval. There has to be at least one place. It says that the derivative at a point somewhere in the interval for this function has to be equal to the slope of the secant line through the endpoints. A lot of different ways that we can interpret this, in terms of things we've talked about already. So let's take a look at what's really going on here. If you look at what's going on, we're talking about the slope of the line through the endpoints. So if I draw in the line through the endpoints here, there's the secant line that goes through those two endpoints. And you can visualize a number of places on this curve where a tangent line to this curve has this same slope. Like right about here is one. Right about here is another one. And right about here is another one. Right about here is another one. And so for this particular graph that I've drawn, there are actually 4 different values, possible values of c, where the derivative of the function at c is equal to the slope of that secant line through the endpoints for looks like 4 different places in that interval from a to b. And of course, that's only guaranteed because the function that you see drawn here is continuous on the interval from a to b and differentiable on the interval from a to b. If it's not either of those things, all bets are off. Can we have places where the derivative is the same as the slope of the secant line through the endpoints? Yes, but it's not guaranteed. And we've talked about that idea with some earlier theorems as well. All right, let's look at some examples. Example number 1. It's 300 miles from my house to Cleveland. If it took me from 2 p.m. to 8 p.m. to drive to Cleveland, then, first, what is the average rate of change of my distance traveled in miles with respect to time in hours? So the average rate of change of my distance is the change in distance, which is 300 miles when I drive to Cleveland, divided by the difference in hours, 8 p.m. minus 2 p.m. And so, doing these little calculations, I determined that my average rate of change for my distance is 50 miles per hour. Now, what does the mean value theorem tell us about our trip? First of all, the speed that I travel in my car has to be a continuous function. My car doesn't just jump from 20 miles an hour to 50 miles an hour. It has to actually cross through all the speeds in between. So, my speed in my car is a continuous function. It's also differentiable. A differentiable function. I don't have any cusp points or corners or anything like that in my speed function. Therefore, the mean value theorem applies to this trip. And what the mean value theorem tells me is it tells me that there is at least one time between 2 p.m. and 8 p.m. when I'm driving exactly 50 miles per hour. All right, that's the mean value theorem in context, in practice. Okay, let's continue on. Example 2, verify that the function f of x equals x cubed plus 2x squared minus x satisfies the hypothesis of the mean value theorem on the interval from -1 to 2. Then find all values of c that satisfy the conclusion of the mean value theorem. So, first of all, f of x is a polynomial. So it is both continuous and differentiable for all real numbers. Continuous and differentiable for all real numbers, comma, so it is continuous and differentiable on the interval from -1 to 2 and the open interval from -1 to 2 respectively. So it meets the hypothesis of the mean value theorem. Okay, that means that it also needs to meet the conclusion, which means we can show that there's some c where f prime of c is equal to f of b minus f of a all over b minus a. Our task here is going to be to find such a value of c in the interval. Okay, so in order to do this, I'm looking for where, let's see, I need the function value at both endpoints, f of 2. If I substitute f of 2 in here, that's 8 plus 8 minus 2. F of 2 is equal to 14. Did I calculate that right? And then f of -1. I substitute -1 in there. That's -1 to the third is -1 plus 2 plus 1. That should be positive 2. Is that right? Right? Yes. And then I'm going to substitute into, or I'm going to figure out what the derivative is. So f prime of x is equal to 3x squared plus 4x minus 1. Okay, I hope all my calculations were correct. Yeah, that looks correct. Yeah, that looks correct. Sorry, I was questioning my own calculations for a second there. So now we want f prime of c to be equal to f of b minus f of a all over b minus a. So that means that we want 3c squared plus 4c minus 1 to be equal to f of b minus f of a all over b minus a. And so let's see, that's 12 over 3. So that's equal to 4. So we're looking for where 3c squared plus 4c minus 1 is equal to 4. We'll go ahead and get c by itself and use the quadratic formula to go ahead and solve this. Or, I can solve it on my calculator, however you want to do it. You know what, I'm not going to use that calculator. I'm going to use this calculator. So let's go ahead and we will graph the function y equals 3x squared plus 4x minus 5 We'll go ahead and graph that. And we're only concerned with any zeros in the interval from -1 to 2. I mean, I can graph it in any window. Let's go ahead and we'll graph it in any window and talk about discarding values. You know, if we look at this, we see that there are two values where this curve crosses through the x-axis, but the one on the left here is to the left of 2, which I can verify if I find that 0. You know, let's go over here. And so that's at -2.120. That's not in the interval from -1 to 2. And therefore, we're not interested in that one. Let's find the other one. Lower bound, upper bound. All right, and we get as our 0 0.786. So C is equal to 0.786 is the only value of C that satisfies the conclusion of the mean value theorem on that interval. Okay? All right, I think we're going to cut it off here. I don't know that I have enough time to get to the next example. And we'll go ahead and we'll conclude this lesson in a second video. All right, see you folks then, and have a great rest of your day.